Questions about anything? So last time I was in the process of using Fourier series to solve the famous Dirichlet problem on the unit disk, which is a very physical problem about finding a steady state temperature, say at a metal disk that's a metal plate in 2 dimensions. So at steady state, the temperature function, by sort of pretty simple physical considerations involving Kelvin's law of heat flow, satisfies the Laplace equation. So the Laplacian has to be 0 on the inside. And the Dirichlet problem, we're looking for the solution. We would expect it to be continuous up to the boundary if the boundary values were a continuous function. And we'll see that that's the case soon. So I want the solution to be continuous up to the boundary with boundary values prescribed. So we've got heaters and coolers on the boundary keeping it a certain temperature. And we know what that temperature is with boundary values prescribed. And what that means is we want u of radius 1 theta to be something we know. So that'll be an f of theta. And that temperature is given. And then the problem is to find a u that satisfies those conditions. Any questions from last time? Let me look at what we did last time. This is last time. So there's the statement. The heat equation is du dt equal a positive constant times the Laplacian. But at steady state, du dt would stabilize to be 0. And so that goes away, and that's how we're left with the heat equation. The Laplacian is in Cartesian coordinates is d2x squared plus d2y squared of u. But in polar coordinates, which is something you learned how to do, there's that heat problem. In polar, so what we're going to do. In polar coordinates, there's the Laplace operator. It's d2u dr squared plus 1 over r du dr plus 1 over r squared d2u d theta squared. And so when we write out the Laplace equation in polar coordinates, it looks like that. And we're looking for a solution that, to use the method of separation of variables, we're going to look for solutions of a special form, r of r times theta of theta. Hopefully we're going to find enough solutions that we can add them up and get a general solution. Okay. Well, I wrote that out last time. There it is. When you stick it in and use the polar coordinates Laplacian, you play some algebra games to put all the r functions on one side and all the theta functions on the other. And if for a function of r to be equal to a function of theta, they both have to be constant. So we call that lambda. Okay. And last time we started with the theta problem, which is we've seen. It's very familiar. We'll save the r problem for the second thing. The theta problem is just the simple harmonic motion differential equation. And in fact, we're going to get trigonometric functions from it. You ask yourself what the boundary conditions ought to be for this problem, and you conclude that what you need the solutions to this problem to be periodic. Meaning, when you come back to theta, you start from theta equals 0. When you come back to 2 pi, they better hook up. Otherwise, you'd be ripping you wouldn't expect your heat function to have a jump. Also, you'd expect their derivative to hook up because it wouldn't have a crease either when you graph it. So no jumps, no kinks. That leads to periodic boundary conditions in place of the usual boundary conditions that we've seen. And we played around and saw that the only time we get the possibility of solving that, we can solve it in the lambda equals 0 case, because then we got a constant solution. And a constant solution certainly can be made to satisfy those periodic boundary conditions. So we got one solution for lambda equals 0, namely the constant solution. And I took the constant to be 1, because later I'm going to take linear combinations of these things and get more solutions. Okay, when lambda was less than 0, well, then you get exponential functions, and you can't possibly satisfy the periodic boundary conditions with exponential functions. You have to write that down and just do it, but you get to a point where, oh, darn, the only thing I can have are those C1 and C2 both being 0. And so you get nothing. You only get the 0 solutions in that case. But good news, when lambda is positive, then we get trig functions. And of course, we know we can make them wiggle just right. So when you come back around 2 pi, they hook up. And since they're 2 pi periodic, you can also arrange for the derivatives to hook up. Okay, and so we realized that, I guess I didn't go into the details, but they're routine. You just write down those equations and make them happen. And you realize you can only do that when lambda is an n squared. So 1 squared, 2 squared, 3 squared, etc. So lambda, we've got... Now, the next thing I'm going to do, now that I know what the lambdas have to be, and that was from the theta problem, now I'm going to start sweating about the r problem. Okay, and the r problem, there it is right there. That's where I ended last time. So that's a quick recap of what we did and where we're at. That is a famous differential equation in the r thing. It pops up whenever you use polar coordinates to study the Laplacian. So it's kind of one of those equations that you can't avoid forever. This is where it pops up. It's called an Euler equation. And you look at it and guess. If you had to guess a solution, you might guess that r to a power would be a reasonable thing to guess. Because every time you differentiate it, the power would go down by 1. And notice the coefficients, the power goes up by 1 every time you differentiate it. So going down by 1 and going up by 1, it would stay r to the p. And that's a brilliant idea. So let's see. What our problem now is... what happened to my... Okay, so here's what I reviewed. And now we have the theta problem. That was theta double prime plus lambda theta of theta needs to be 0 with periodic boundary conditions. And that requires lambda to be either 0, 1 squared, 2 squared, 3 squared, etc. I did the lambda equals 0 case, and I got, let's see, what do we get? We got lambda of 0 of theta is the function 1. And the lambda of n of thetas I'll use Fourier series notation because it'll be, we got n thetas, cosine n theta and sine n thetas. Okay, that's what we did last time. And now we're going to do the R problem. It's an Euler equation. Which means, let's see, what is it? It's R squared, R double prime, plus R, R prime, minus n squared R equals 0. And here we're going to allow n equals 0, 1, 2, etc. Those are the lambda. And remember, the lambda was equal to n squared. Okay, so Euler's big idea is try R of R equals R to a power. Then, of course, R prime of R would be P to the R of P minus 1. R double prime of R would be P times P minus 1, R to the P minus 2. And the typical thing in ODE is plug it in and try to force it to work. So plug it in and force it. Of course, this is in the books because it works. You can force it. If it didn't work, it wouldn't be in the books. All right, so when I plug it in, I would get R squared times R double prime. That's P times P minus 1, R to the P minus 2. Then I get plus R times R prime. That's P times R to the P minus 1, minus n squared R, that's R to the P. And I want that to be 0 somehow. And sure enough, those powers come back up to R to the P in every case, and I'm left with stuff that are just numbers, P times P minus 1 plus P minus n squared R to the P. I want that to be 0. And of course, except at the origin, R to the P is never 0. So it's clear that we need this to be 0. We need that equal to 0. And that's just a quadratic equation in the power. So that, in fact, we're going to get two solutions out of this. Okay, so we need, this thing is called the characteristic equation for the Euler equation. Characteristic equation. It feels very similar to what we did when we did the constant coefficient second order equation problem for an Euler equation. Okay, so what are we going to get here? Let's see, that would be P squared. Oh, look at the P's cancel. P squared minus P plus P. So it's P squared minus N squared equals 0. We get P is equal to the square root of N squared plus or minus the square root of N squared, which is N. And so we get two solutions. Namely, R to the plus N and R to the minus N. They're clearly linearly independent. When you studied linear differential equations, second order, you needed two linearly independent solutions. So these are clearly, why are they linearly independent? One is certainly not a multiple of the other. So these are clearly linearly independent. Last time I computed the Wronskian to show that I could solve any initial condition. I could do that again. But the theory says if they're linearly independent, that Wronskian is going to be non-zero. So they're clearly linearly independent. Which in the case of just having two functions, one is not a constant multiple of the other. Or you could check the Wronskian. The Wronskian is non-vanishing. Remember what the Wronskian was. The Wronskian, I guess I didn't want to do this, but I'm going to do it anyway. The Wronskian is equal to the determinant. You put the functions in the top row, and you put their derivatives in the bottom row. N times r to the n minus 1 minus n to the r to the minus n minus 1. And sure enough, you calculate that, and it's not 0. Something bad happens at the origin, but we don't care about the origin. But now I'm going to tell you we do care about the origin. Sorry. Because I get... so that's good news. So R of R, the general solution to that would be A r to the n plus b r to the minus n. But if you think about it, what would that mean about my solution? R to the minus n blows up. So this part here is ouch. That would make my temperature hotter than hell. Or maybe colder than too cold. So the temp blows up. There's no, these constants could be negative. So ouch, it blows either up or down. Temperature blows up at the origin. And so we're going to use physical considerations. If you make the boundary of your room 15 degrees, or in some temperature range, there's no way it's going to get hotter than hell in the middle of the room. We know temperature doesn't behave like that. And in fact, if you start thinking in terms of Kelvin's law of heat flow and conservation of energy, etc., so we're going to rule that solution out. We conclude that we need the B to be 0. Via physical considerations. Physics, conservation of energy, etc. If you pump in a finite amount of energy, you're going to have a finite total energy. Can't be blowing up like that. Okay, so this is good news. We get, well, let's see. The n equals 0 case, let's see. What would I got? I guess I should do the n equals 0 case separately. What was I going to get? P. You only get P. Oh, yeah, I remember now. Remember the reduction of reduction of order thing when you only get one solution. So let's see. For my Rn, I'm going to get a constant. But let's see. So let's take a constant. Just the A times R to the n. And remember my theta n was an cosine theta plus bn sine theta. Sine n theta. I'm going to multiply these two things together. I'll call it u sub n of r theta is going to be the multiplication of those two things. And notice I would have an a times an an and an a times a bn. So I'm going to take that a to be 1. When I multiply those together, I get r to the n an cosine n theta plus bn sine n theta. Okay, and let's see, the n equals 0 case. You would get only one solution. That was p squared equals 0. So that way I only get the constant solution. Get the power is equal to 0. One solution, r to the 0, is the function 1. And it's an ODE fact that you can do reduction of order. You can do the method of reduction of order, which I might review. It's an ODE thing. It's worth reviewing at some point. Reduction of order, you get a second solution. When you do it, you get a second solution, which turns out to be log of r. And that's a bad one. It blows up down. It blows down to minus infinity at r equals 0. So bad at r equals 0. So we toss it, like we did the previous one. And so the lambda equals 0 case, I get r0 of r, the function 1. And my theta 0, let's see, we also had theta of 0 as the function 1. And so my the one corresponding to 0 u of r theta is just 1. And in fact, I'm going to take it to, well, let's see. I'm going to take it to be a constant, because I'm going to take linear, so notice, this is a linear problem. Laplacian u equals 0 is a linear partial differential equation, meaning I can add solutions together and get more solutions via the superposition principle. So I can take linear combinations of solutions and get more solutions. So the superposition principle holds, meaning I can take linear combinations of solutions to get more solutions. Linear combos of solutions are also solutions. Okay, so we get gobs of solutions. So I can, of course, linear combinations are finite linear combinations. So I'll take my constant times my zeroth one. I'll call that constant A naught, obviously, because I'm thinking Fourier series. And this is now a trigonometric polynomial. Those satisfy the problem. And now, so let's see, that satisfies all the boundary, the periodic stuff. It satisfies the differential equation. The one thing I haven't considered yet, and finally, consider the boundary conditions. So finally, we think about the boundary conditions. Well, the boundary conditions are when I stick in R. Oops, I skipped my R to the N. This is important. R to the N goes there. That was. Did I skip that before? No, there it is. UN of R theta is R to the N. Okay. Finally, we think about the boundary conditions, and that's U at R theta. U at 1 theta that's just a partial sum of a Fourier series. And we realize, that's where I better let this N go to infinity. Like we did with the vibrating string problem. That's what we want. So of course we're sunk unless that happens to be a trigonometric polynomial, which in your homework, in the case that that's a trigonometric polynomial, you can just look at it and say, aha, I know what I need those coefficients to be. They're determined by that. So that problem, asking you to solve the heat problem when the right-hand side is something simple in terms of sines and cosines, you can just do it by looking at this and saying, yeah, I know what the A's and B's have to be. And I only need finitely many. So it's not an infinite sum. But if that's not the case, we need N to go to infinity. And so hopefully that's going to lead to something. And in fact, when we do that, the A ends and the B ends are the Fourier coefficients. So here's the summary. The solution to the Dirichlet problem is, I guess I have to write it again. This time I have to let it go to infinity. Okay, I have to let this go to infinity now. And this is going to be the U of R theta. Where the coefficients are the Fourier coefficients for the boundary conditions, for the boundary temperature. Where the coefficients are the Fourier coefficients. For the boundary function f of theta. Okay. Here's a fascinating thing. So that solves the Dirichlet problem. All those things were harmonic, so when you add them up, they're going to be harmonic again. So the solution's harmonic, and we're just going to hope that all these things converge and it really does happen. Of course, it's going to do that. Here's a fascinating consequence of the formula. Fascinating fact. Here's A naught. When I stick in r equals 0, that's the value at the origin. So that's equal to the value of u at the origin. And that's, of course, equal to 1 over 2 pi integral from, you can take an integral over any thing of length 2 pi. But I guess we'll stick with minus pi to pi. I could go 0 to 2 pi. Why don't I do that? It doesn't matter. Remember that fact about periodic functions? You can just take any old interval of length 2 pi. And that's the integral of f of theta d theta divided by 2 pi. That's the average of f on the boundary. That means that harmonic functions satisfy the averaging property. Their value at the center is equal to the average on any circle. This is the averaging property. I could have taken a circle that's not of radius 1 and gotten the same consequence. So harmonic functions satisfy the averaging property. I would say this averaging property. On circles. And so that's why you think of temperature as sort of being a diffusion problem. It spreads out in such a way that the average at any single point, I mean, the temperature right here would be the average on a circle, and it could be any old circle. Or I could take, in fact, I could take the average on a ball about it, and that would be the case also. And it's a fascinating fact that characterizes harmonic functions. It turns out if I had a continuous function that satisfied that averaging property, it would be differentiable and satisfy Laplace's equation. That's kind of a mind-blowing thing, to start out with continuity and end up with something differentiable. At various times when I teach this, I can't resist doing this calculation, but maybe I'll resist this time. So there's a fantastic calculation. Let's see if I can do it here. I'll summarize what it is. Okay, so we got u of r theta is equal to that thing. Remember the when I turned real Fourier series into a complex one. the complex version, so let's see, I would get u of r theta would be a naught plus the sum as n goes, let's see, there's going to be n goes from minus n to plus n. Here I'd get the r to the n's are oh blast, sorry. I'm sorry, I should stick with my notes here. N equal 1 to n. I have r to the n, an. Remember, cosine n theta is e to the I n theta minus e to the minus I n theta over 2 plus bn. Sine of theta is e to the I n theta minus e to the minus I n theta over 2i. When you put it all together, a naught is the same. It's the average. And here now, let's see, when the n's are negative, I'm going to get, I guess I'm going to summarize what I get.
Is the first one plus?
What?
The first one, should it be e to the...
Plus. That's cosine. Right. So let's see. I guess I have to write this mess here as this is going to be r to the n times an minus I bn over 2. That was C plus n. And the other one is plus an plus IBN over 2. This one's times e to the plus n theta, and this one's e to the minus I n theta. And this was C minus n, the complex Fourier coefficient. And so I claim that what you get is that this is a naught plus, this is a plus, this is going to infinity, plus a sum as n goes from minus n to minus 1. That would be r to the absolute n when you've got negative numbers there. Cn e to the minus, let's see, in, those are negative ones. And then we get the positive ones. Those would be an r to the n, Cn e to the in theta. Anyway, let's see. R to the, yes, this is a little n here. Oh, let's see. Okay, so when you mess around, what you realize is that I get a very simple formula. This, now I see, remember. I want this to go to a finite thing, so I'm going to make that an n. I'll call this u sub n. It's a finite sum there. Anyway, you monkey around with it, and you get that this thing is expressed as a sum from minus n to n. And the only thing that's different here is you get an r to the absolute n. Meaning when it's positive, it's r to the n. When it's negative, it's also r to the n. Okay, remember what those CNs are. That's a sum of, I'll pull the r to the n out. And the CN here is 1 over 2 pi integral from 0 to 2 pi f of t e to the minus int dt. That's the CN. And then we're going to multiply that whole mess by e to the plus in theta. Okay, so what's the obvious thing to do here is to put that inside the sum, and then you realize, oh my gosh, I've got a geometric sum. So this mess turned out to be integral. When I change the order of sum, I get the integral from 0 to 2 pi of something very concrete. R to the absolute n, e to the I n theta minus t times f of t dt. And that's a geometric series. It's actually, there's two of them. So this is just a sum of two geometric series. It's a sum of two geometric series. Let's see, we get a 1 over 2 pi. The first one is the sum from 0 to n, and the second one is the sum from minus n to minus 1. But the thing is, you can use the formula for the sum of a geometric series. Let's see, what are the terms? I would set W equals, see, we've got r to the n's there. We'd have an r to the n, e to the I n theta minus t. Would be one of the, that's that thing to the nth power. And when I have a minus one, so let's call a W twiddle would be the other one, that would be r to the absolute n, e to the minus I n theta minus t. That would be an r to the minus I theta n theta minus t. That would be r to the theta minus t to the n. And so we have two geometric series in those things, which you could sum explicitly. Okay, it's not hard, easy to sum explicitly. And then do some algebra. Do some clever algebra. Not terribly clever, you just sit down and do it. Do some clever algebra. Kind of like we did when we got Fayer's kernel and the Dirichlet kernel. Like we did with the Dirichlet kernel. In fact, this is the same Dirichlet. I did it carefully once and don't think you'd enjoy seeing me do it again, like we did with dn of t. And we get something incredibly simple as we let n go to infinity. We get this famous formula called the Poisson formula for the solution to the Dirichlet problem. Which is that u of r theta is equal to 1 over 2 pi. That thing sums to be something very simple. Let's see, it's 1 minus r squared over the absolute value of r e to the I theta minus e to the it squared f of t dt. That thing is called the Poisson kernel. So we went through this Fourier series business, always having doubts that maybe letting n go to infinity wasn't quite allowed. Well, once we do it and mess around and simplify the formulas, we realize we get something concrete, and it's easy to show that this thing solves the problem. So, a mind-blowing fact, all that crazy stuff we did, forget you ever saw it. So forget about questionable math, questionable things we did, like letting n go to infinity, etc. Like letting n go to infinity, etc. This concrete thing can be shown to solve the problem. Another thing I haven't shown you is the nitty-gritty algebra of adding up those geometric series shown to solve the Dirichlet problem. So, for example, it's harmonic in r and theta. You can differentiate, or r and theta. You can differentiate under the integral sign. It's a very clean, nice formula that you can do stuff like that with. And so you can differentiate under the integral sign and see, sure enough, that's a harmonic function. And the thing that you might think would be hard is you want to show it tends to the right thing on the boundary. And the key to the boundary conditions, so an easy thing, I can take the Laplacian under the integral. So u is harmonic. That's an easy thing. Showing that u of r theta tends to f of theta. The key to that, the Poisson kernel is a good kernel in the sense of Stein. It has a big bump where it's supposed to. The area underneath it is 1. It's positive. It satisfies those 4 conditions. And so it's a good kernel. And that's just, I can demonstrate that just by looking at the formula and saying, sure enough,